every time I talk about it, it's such a subtlety of saying here going forward versus there going backwards, when we were talking about. So again, let's simplify. So I always say physics and statistics are very closely related, and biology and ABM is very closely related. So what is the difference between the two, and why the approaches are completely different, even though it comes to it looks so similar?
Yeah, maybe I'll say this, that I think there are many things in physics that do think about sort of unit level. If you think about how physics has broken things down, it just happens to have started with some very big things, right? So if you think about, and those things worked, if you think about Newton's laws of motion, they did really well until sort of Einstein came up with his relativity and all that stuff. If you think about planetary systems and how that needed to work, I think there were some really good equations which helped us. E = mc squared was another big part of it. So I think the way physics started, I think it was a lot more top-down with bigger things, bigger pictures, bigger objects. And so these things were good enough to explain because the minute differences probably didn't make that much of a difference.
Yeah, and we'll hold off on quantum computing in a minute.
Yeah.
but keep going.
Yeah, so the minute differences probably didn't make that much of a difference because of how the practicality of it, we probably didn't care. But now, if you think about, well, you're actually trying to send a man to Mars and how precise it needs to be. Well, they'll need to get down to the fundamentals of like how everything is working, right? So sending a man to Mars is absolutely no trivial, and they need to account for everything. There's top down, there's bottom up, there's everything that needs to be included. So I think physics is going to get there. It's already doing a lot of these things. But biology, fundamentally, how it started out, it was always about a human being, right? I think it started that by... Or a cell. But you couldn't explain something in a human being by looking at it. It was very hard to do it.
So you can't look from the outside of a human and figure out the inside.
Right? So that's why as doctors were anyway, right, there were different kinds of doctors. There were doctors for the heart. It's different from the doctors of the legs and the muscles and the blood and so on and so forth. So by definition, when you cut open, you see these small little things. And it's hard to think about it at an overall level from a biology standpoint. So I think the way they developed, they just happen to be on two ends of the spectrum. And I think as you I'm sure you agree, and a lot of people have said, fundamentally it has to get towards a common point. They just happen to be coming from two different places given how the entire development in human history happened.
So let's walk through biology. So DNA. Now we have the COVID vaccine using mRNA. And I also really understand that you're going from such a tiny level of information. And actually, yes, there's a lot of information in DNA and mRNA, but it's actually very, very simple building blocks, right? Similar to, I don't want to go too far into fractal theory and chaos theory, but there's a lot of relationship between this, where Y is, and there's going to be some times where the genetic structure has an abnormality and creates certain types of diseases and stuff like that. Walk us through. So we've all seen that video where you've got the first single cell of an egg, and then it starts to split into all these different cells. So walk us through how ABM could almost simulate this kind of like emergent human through understanding very small fundamental algorithms of like DNA or whatever.
Yeah, and that's something that I think a lot of people are trying. I think there's still ways to go on something like that. But I think when you look at something that small, one of the things that's very hard to do is make it supremely complex. Because when you start saying, hey, it's one cell, single cell organism and stuff like that, then I think in some ways it's very hard to say it's capable of exhibiting extremely complex behavior in and of itself.
Yeah.
I think what you are almost forced to do, which is a good thing, is to say, hey, what are some fundamental things about that? What is it trying to achieve? And is there a way to simulate that? I think that's where what people have tried to say is, hey, when you think about a cell, what is it looking to do? Survival, food, growth, reproduction, and stuff like these things, right? And if you start looking at that and add to it a little bit of DNA, which in some ways is a guiding element of how things should proceed towards the ultimate goal, right? In terms of what the body will look like, how the mind will look like, how will this all sync together. Some fairly simple things can start creating some complex organisms, right? Now, a classic example of this was, I think this was The Game of Life, was One Newman or something like that, where, hey, small things could create some massive things which were self-sustaining. So just that gives you an idea of how simple rules can create something complicated which is self-sustaining, right? And this is something that people can go look online and it is amazing the amount of complex sort of behavior that can come out of it. And to me, when I think about biology, going back to your question, I think simulation for the sake of it, for sure, great. But I think where ABM for me really helps is what are the environments, what are the rules maybe, right, that are required for this to happen? And that gives us all a fundamental understanding of how biology may work, right? To give you one another way, a simple example going to neural networks, right? We all knew there were cells, neurons, and there were synapses. And if you think about it, that itself has been the foundation of deep learning. Like, as crazy as it is, all it is a cell with synapses to other cells. And that helped us understand so many things. And that's why I think going down to the biology and understanding, hey, simple rules, what does it need for it to multiply?
Yeah.
Right? You can try out a bunch of things, be wrong in some simulations, be correct in some others, and seeing if it ultimately builds towards that. That's where the foundational truths come in, right? I think that's where you start simulating a lot of these things and taking it from there.
So, machine learning, it's been the buzzword
forever.
Well, it feels like it's forever. It hasn't even been that long, relatively speaking, at least from the computational.